I'm John Boyd. I'm going to talk about code reviews. And somebody mentioned earlier that I'm talking into the sunset. So if I'm distracted, it's because I'm marveling. I'm from Seattle, and I'm watching the sun, which I haven't seen in weeks, go down. It's so beautiful. Before I jump into this, I'm curious, who am I talking to? How many people here are developers? I write code. Testers, some of my tester brothers out there. Oh, yes. PM, marketing, management. Okay, excellent, excellent. Welcome. So I was reading the bios of the other speakers here, and there are some awesome people. I think Justin Bieber was here. I'm not sure. But I noted that Huh? So you saw him too. So I didn't introduce myself on the speaker bio, so I'm going to say a few words about myself. Well, I'm John. I'm a senior security engineer at Security Innovation. I break things. Coolest job ever. Before joining SI, I worked at various companies, Disney, Microsoft, Veritas ended up getting bought by Symantec. I have an undergrad in computer science and a master's in software engineering. So not only do I like to break things, I like to write code to break things. And we're going to see that here in a few minutes. I have a CISP and some other certs. All right, so this is what we're going to talk about. I ran into a problem, and I'm going to explain kind of what that problem is, some of the things I tried, and what worked, what didn't, and we're going to talk about some patterns of how things fail. And for me, this is why I got into computers, was watching things fail. So let's give this a shot. You know, I did my undergrad, grad school, but I went to high school at a school in Maine called the Maine School of S&M, and it's science and math. And while I was there, I took a course in C++ and algorithms and data structures. And towards the end of my cycle, I wrote a program that read in a text-based maze and parsed the maze, and then I wrote some AI to solve the maze and print out the result. And when I turned it in, I felt like a god. I was amazing. I am the best programmer ever. Fast forward a little ways. I did my undergrad, and in my undergrad, I wrote a program. It's about 2,000 lines long. It was a kernel mode network time synchronization protocol, complete with kernel mode driver, user mode service, sockets, integration into Windows. It was a little tipsy, but it worked, and I was proud of myself. I was like, this is even better than the maze solver program. Fast forward a little bit further. Went to grad school. Started consistently writing programs and projects that were 20,000 lines long. I wrote a network backup product with encryption and distributed objects and database backends. And I realized that was about the limit of the amount of code that I could page into my brain at one time. Like, that was it. Anything over was something else. So these days, I work on assessments. I break things. I also do a lot of code reviews. And it's not uncommon for somebody to come in and be like, here is all of our code. Find vulnerabilities. And I'll do a word count or whatever, and it comes back with 5 million lines of code. And my little meat brain kind of overloads at that point. I'm like, I have no idea what I'm doing. I don't help. And ultimately, it comes down to looking for a needle in a haystack. So what do we need? Magnets, right? How do they work? So we're going to talk about magnets. So what I tried, first thing I tried was, getting a list of all the files and opening up the first file and reading it line by line by line. And that didn't go well. I may have passed out, we're not sure. So then I tried some kind of basic scripting, let's see what I can do. Then I tried some really super duper advanced scripting with AI and scary algorithms that I learned in grad school. And it turns out that worked a little bit. And then I did some more parallel optimizations to that and more targeted scripting. And this is kind of what we're going to talk about here. Oh, right on. So I mentioned that reading line by line, file by file. Is Srini here? Oh, I was hoping he'd make it. So kind of what I had initially thought would work was I'd read line by line, file by file, and I'd assume that if it was insecure, I'd know it when I saw it. But it's perhaps a little bit true. I mean, I do find patterns of insecurity, but maybe not so much. So I decided, I'm going to start writing a script to try and find vulnerabilities. And when I did this, I needed to know what were the exact patterns of things that were going to break. What exactly is SQL injection or cross-site scripting, and what are those across? Like, what are all of the ways that a developer can shoot themselves in the face or foot? Sorry. And so in a former life, I had worked for Microsoft, and when you're at Microsoft, you drink the Kool-Aid, and the Kool-Aid says that anything written in C# is secure. And so, I was on a C# project going and trying to think of all the ways that a developer can shoot themselves in the foot in C#, and it turns out you can do it. So I went through and started enumerating, what are the things that I can do? And the first place I go is the OWASP top 10, and the top 25, and then the CWE list, looking for basically inspiration on what are some patterns that I can grep for, what are some patterns that I can look for. So let's play a game. Let's assume that we've got an ASP.NET website and page validation is turned off. So if I throw in some cross-site scripting, it's not going to pop saying this is a dangerous query. And let's say I've got 5 million lines of code, and I grep for response.write and star.cs. I'm leaving out the syntax of recursive and stuff. Pipe2 grep for request. And this will find that. So when I first thought of this, I'm like, okay, I'm on an engagement. Nobody would ever do this. Like, this is the wrong thing to do. And it turns out that some developer had left in some debug code, and I was actually able to file an issue on this. Like, hey, maybe there's another way of doing this. It doesn't find stuff like, let's take the user input and assign it to a string, and then somewhere later we're going to, declare a variable, string type, assign it to evil user input, and then later on in the code we'll write that out. So I think the buzzy jargon is, the source and then the sink. So I thought, well, gee, I can solve that. Let me do a little bit of C# magic and extract all the variables that are assigned user input, and then extract all of the lines that represent scary method invocations. So things like process.start, response.write, file.delete. There are a bunch of things where, if a user gets a hold of it from user input, he can mess up the server. And then, from there, I was able to say, okay, for each evil variable, I'm going to call it evil variable, something that has user input. For each scary possible method, does the line contain scary method and evil variable? And it turns out it kind of works. I mean, it's not Fortify or check marks or one of these super static analyzers, but it kind of works. And it works particularly well for PHP. And I'm like, oh, okay, well that's interesting. But it fails for larger scenarios. Like, let's say that I take user input and assign it to a variable, and then invoke a method on a different class in a different file, not in this file. grep will not find that if you're just grepping through files one at a time. So, fail. So when I realized this, and I started kind of going down the rabbit hole, I started writing code to parse code. Now, I write code the same way every time, and my code is super maintainable and easy to read. I mean, I'm not really that smart, so I don't try and get fancy. But it turns out a lot of developers measure their self-worth in the ability to write code that I can't read. And if I can't read it, my code trying to parse their code is not going to make it. It's like, it fails. Who writes an inline delegate for an anonymous? No. So I was trying it. I tried it again. It wasn't working. And I ended up at DEF CON. And one of our guys, Dennis Cruz, sat with me at DEF CON. And he's like, what you need is something that will generate an abstract syntax tree. I'm going to talk about an abstract syntax tree in a second. But we sat down over coffee and had a 2-hour conversation on code parsing and code analysis. And he pointed me to a library, open source library, I think. Yeah, pretty sure. Called InRefactory. And what InRefactory will do is it will read in source code, and it will kind of annotate it for you into something called an abstract syntax tree. And all that is here's the source code, Well, we'll talk about that in a second. Basically, during that conversation, there were some finer points of doing static code analysis. And these are some of the finer points. And we're going to talk about each of these. And then he ran out of oxygen and passed out. I don't know what happened. So, abstract syntax trees, being able to create a graph of flow through the code, like this function calls this function, calls this function. And then, figuring out where the data is flowing from this user input through this function, through this function, through this function. And then being able to write some AI or some state space search algorithms, and again, we're going to talk about this in a minute, to be able to trace through this. It sounds easy, right? So I mentioned abstract syntax trees. And basically this is code. And then what is this code? So for example, this is a method invocation. This is a class declaration. This is a variable assignment. This is a variable or object initializer instantiation. So using this, I went through the source tree and I read in each of the files and created these abstract syntax trees. So I created a disjunct forest data structure. I am a software engineer by training, and I like algorithms. Like programmers write code, software engineers implement algorithms. So basically I got a forest of these abstract syntax trees. And my next step was, well, now I need to link these together. I have nodes that represent class and method. And then inside that method, I have all of the invocations. And each invocation points to another node in another class. So, what do? We connect the dots, right? And in this, we're creating a control flow graph. So for each node in this tree, figure out what class does it reference, what method in that class does it reference, and then make a link to it. And in this way, we can kind of create a CFG. So the code for this is actually pretty complex. Oh, by the way, I'm going to show you guys some tooling after this. One of the awesome things about what I do is I get to open source everything that I do. So all of this is on GitHub. I'm not like trying to sell a product. This is actually open sourcey stuff. So let's talk about state space search algorithms. Let's say that we've got this graph of, this class, this method invokes this class, this method invokes this class, this method. What we'd like to be able to do is find from the source to the sink and be able to trace through this. And what we need to do is implement some AI. And when you start talking about AI, people are like, oh, that's scary. It's going to take over the world and imprison us. And no, it's actually just another set of algorithms, albeit cat-like algorithms. So there are a couple of different versions of state space search algorithms. For example, you have a depth first search. Let's say that you're starting at the top. Let's say this is a node for user input. And you take the first node, the first method invocation. And then from there, you look at all the method invocations and take the first one. And then from there, you take all the method invocations and take the next one. And let's say that there's some evil, function like process.start that you were passing this user input through. Here, you just, print out an error message, or not an error message, print out a message saying, hey, you know what? We know what the call stack is. And we think there's something wrong here. You should probably be doing something less scary. But there's an alternative. Breadth first search. So in this, you have, you're starting user input, and you take the first invocation, check to see if it has anything. Nope. Take the second invocation. Does it have anything scary? Process.start, file.delete. Nope. Okay, now let's go down a level. Any of these? Down a level. Oh, we got a process.start here. Let's throw an error, or let's write a vulnerability. So for completeness, there's an additional algorithm, and this is A star. And this is really a heuristic-based search algorithm, similar to the first two, except where the first one might be implemented as a stack, and the second one might be implemented as a queue. This would be implemented as a priority queue, where the closeness by some heuristic to user input might be some function. So I'm not going to talk about this. This is not useful for what we're talking about, but I include it for completeness. So now we have a graph, and we have an AI that can traverse this graph. We need the AI to understand good versus evil. And we see that evil is a new SQL command, or a new process, or a response.write line. And these are just rules. that the AI fires when it reaches a node. Like, hey, does this rule work for XSS? Are we passing it to enable XSS? So the result, and again, this is all open source, so we'll get to that in a minute, is we have a script that searches the file system for source code, parses that source code into a usable graph, and then queries that graph for vulnerabilities. And if it finds something, it'll give you a stack trace of, hey, here's the user input. It follows through this function, this function, this function, and here's where it's doing something scary. So there's good news and bad news. The good news is it works. It does find security issues, and it doesn't require that the source code compile. There's no reflection. So for example, fxcop, it actually relies on reflection, at least in C#. The bad news is I ran it on 20,000 lines of code, and it took 8 hours. Who here wants to wait for 8 hours to determine if there's an error? Right? I didn't either. I was like, oh man, this is so slow. I'm a bad programmer. But we live, we learn. And oh, cool. It turns out that there's some optimizations that I was able to make in kind of an alternate version of that. And I'll talk about that. But what I'd like to do now is give you a live demo. So, who here thinks it's going to pass? Is it going to succeed? Yes, somebody believes in me. All right, let's give it a shot. So for those in the know, static code analysis tool, SCAT. No, actually, cool question. Is it a Visual Studio plugin? I thought about that after I wrote this. And so one of the things I'd like to do in the future is extend Visual Studio to do this. But for now, it's just a Windows Form application. And bear in mind, I'm a penetration tester. You know, I know how to write code, but you know, if you want fortify or check marks, you know, there are other people that you can talk to. So what I'm going to do is I'm going to open up a source file. I'm sorry, not a source file. I've written a web application called Oops. And don't crash, don't crash, don't crash. We're going to run this tool. It scans the source code, looks for vulnerabilities. It runs this kind of AI algorithm. I have some debug stuff here. You can pretty much ignore that. But let's take a look and see what it found. Various informational, medium, and then you should probably look at this. So you can navigate down. And over here you can see something that looks a lot like a call stack. And I never really understood what a call stack was until I had to write one, and now I understand why it's from the bottom up. But if we look at this, let's say this, we can see that it is taking username and just blatantly concatenating it into a SQL command, originating from a page.load. So yeah, we can kind of look around. This does have the simple rules. You remember where I said, let's just see if we can parse out the variable names without having to do the whole abstract syntax tree stuff, because that's faster. So a lot of these will actually show up twice, because it found it one way and it found it another way. So that is the static code analysis tool. This is on GitHub. You can laugh or point at the code, but you can't do both. All right, so let's move on. How much? Yeah, I got plenty of time.
So John, this is only for the C#?
So this says C#, and it does a little bit of PHP. And we're actually going to talk about something a little cooler, not cooler, different in a second, where we're going to start dipping into native code. Cool? Excellent. No Java support, but only because I haven't really been on a Java project where I can run into cycles where I can do it. I mean, I'm hoping someday I'll have the opportunity, but so far, not so much. Yeah, the next one. All right, so we discovered that it worked, but we discovered it was really slow. one of the great things that, and I think I mentioned this about C# 4.0, is there's some awesome parallelization libraries. And I used to write kernel code for Windows, and I've written a lot of things with threads and mutexes and semaphores and kind of thread synchronization primitives. And that code gets ugly fast. It's incredibly painful. It turns out that there's a library that just parallelizes everything. And so I started making use of that. And Mark can actually speak to that. I like to parallelize everything. Parallelize all the things. My life is an abuse case. What can I say? So my next projects turned out to be native code. And in native code, I started dipping into C and C++ for Linux user and kernel mode code, and then kind of the Win32 Windows platform user and kernel mode code. So my goal was to go and find vulnerabilities in those. Here's a bunch of C written for Windows kernel, or Linux kernel or whatever it is. Whoever wants to extend it, have fun. Okay, so when all you have is a hammer, everything looks like a nail. So I start by going and enumerating what can go wrong. And I mean, there's a lot of stuff that can go wrong in native languages. Well, how do I enumerate user input? How do you enumerate user input off of a custom dev control in a driver? How do you input or get user input from a custom ioctl in the Linux kernel? Or an arbitrary file read? And I started realizing that there's so many ways of getting user input that I can't possibly do that in the amount of time that I have. You have 5 minutes, you implement a quick class, you can't do it. So, you're enumerating user input. No, I mean, that's kind of a bust. There's also no safe AST generator. I mentioned that Dennis had pointed me to in refactory. Well, there's not one, freely available for C++ or C. I could write one, but that's incredibly painful. So, I was reading some code, and I realized as I was reading through this code that this code was less secure than WebGoat. And I had to ask, I had to step back and ask myself, was it developed by C programmers, or was it developed by Java or C# devs, kind of the managed guys that don't really understand the intricacies of writing native code? And one of the, as I was looking at this, I started to realize that a metric for how safe or how secure a product is how many stir copies. I mean, I looked at one thing where there were 3 stir copies, and there were comments above them saying this has been reviewed by so-and-so on this particular date, and it looks okay. Another one where there were 1,000 stir copies, So I don't have an AST. I don't have user input. I'm doing it on, a kind of a cross-platform in native code. So I started thinking about what were some of the patterns that I can come up with? What are some of the patterns that I can think of to cause a failure? And so these are some of the patterns. I'm going to briefly talk about these, and I have another script that I need to integrate with this. But, we're going to talk about insecurely executing commands. Unicode stack smashes, race conditions, deadlocks, and some other stuff. All right, so let's take a look at the first one. This one I've actually been seeing for several years, and it's kind of weird. Let's say that you have a product. This is a hypothetical product, but let's say that it's running as root on a system, multi-user system, and maybe it goes to each of the home directories, and it executes the first line of code, ls-l, pipe 2. Maybe it's looking for, excess file usage or something, I don't know. But it's doing something on each home directory, management. What's wrong with the first line, right? So let's say that the path, let's say it's running as root, let's say the path is .:bin/ or :user/bin. But if there's a file named ls in the home directory, it's going to pick that up and run it as root. This is scary. Okay, so let's fix this. Let's say, let's actually hard code. So this is one of the patterns that I'm looking for in native code. Like, it doesn't require user input. It doesn't require user output. But let's fix it. Now we have /bin/ls. And that doesn't fix it either, because they're piping it into awk. And Well, if I just have a program called awk in the directory instead of ls, we fixed part of it, but we didn't get it all. So let's take it a step further. Bin ls, pipe2/bin/awk. And the question becomes, why are we using a system to do this? Right? I can't tell you, but they removed the entire product and had to rewrite it. So the question was, who has dot in their environment path for root anyway? Speaking of which, cool Windows example. Where does this DLL come from? Like, is there a safe, trusted path where you go and find DLLs? Is it just the current directory? Is this, is there even an MD5, or not an MD5, a hash check of this to see if it's been modified? No, it's just, hey, let's load a library that's right there. So in native languages, you would do a malloc or a free. And malloc, it turns out, can return null. New might throw. But let's say that you're looking at something in a kernel mode driver for Windows, and this is effectively a malloc, except it's a different kind of malloc. So what we're doing is we're allocating a buffer, and we're setting the 0th byte to hex 41. In a low memory condition, this will return null, and this will result in an access violation, which will cause a KE bug check, which will blue screen the box and effectively denial of service it. But it turns out, you can totally do this with, malloc or, sysallocate string or stirdupe or any of these, and it's kind of a fairly easy check. Like, did you actually get the memory? This one's actually kind of cool. String copy, stir copy is bad, right? Like, it's still bad. It never started being good. But it turns out, I'm gonna look at this one a little more carefully. Unicode conversion. Let's say that we need 1 byte to represent a character, hex 41, versus 2 bytes, hex 0041. So a wchar, for those uninitiated in systems programming, is 2 bytes per character, dest of 256. And what we're going to do is we're going to take some user input string as an ASCII string, and we're going to convert that to Unicode. So multi-byte to 2 bytes. And we need the size of the buffer they're going to copy into this. So the size of dest is the size of dest, which is 512. Size of returns the number of bytes. Which means that they're passing in 512, saying this buffer is 512 wchars, because this reads it as wchars. This is returning the number of bytes. So if you have a properly crafted user input, you can do a stack smash during a Unicode conversion. And I used to think that stack smashes could not be exploitable. And then I went to a class by a gentleman back here who disabused me of that notion. Sorry to put you on the spot. We just talked about that, I think. Yeah. Let's give another example. And again, I'm showing you these examples, and I'm going to get to a point here in a moment. But let's take a look at this. So we have a function, handle request, and we get into the function, and we're going to enter critical section. So this is lock, or mutex.acquire. And I mentioned that this is hard to get right, which is why I was so happy with the parallelization libraries in C#. And then he took a breath. So let's say that A fails. We leave the critical section, we unlock it, so the next thread can come in and we return. And let's say we do some other stuff. Let's say that B fails and we just return. Let's say that by the end of the function we leave the critical section and we're done. So there's a bug here. Right? So if B fails, we don't leave the critical section. Ultimately, this can result in a deadlock. If I can exercise B fail and get through this, I can deadlock a system, and depending on what service this is running in, I may be able to hang the entire system, or just deny service to that particular, or deny access to valid users for that particular service. So it occurred to me that as I read through various projects and I'm looking at source code, I should probably come up with regression testing. I used to be a tester. Best days of my life. Anyway, used to be a tester, and as I'm reviewing code, I realized that I need to have regression tests for this. So I created basic rules similar to the ones that we saw in the static code analysis tool for parsing C++ and C, looking for these particular patterns. I skipped over one of the patterns because I don't really want to talk about that. But it turns out that because I was able to write these in a way that used these C# parallelization libraries, I was able to go through about 2.9 gigs of code in about 10 minutes. So no more 8 hours for 22,000 lines of code. I'm not sure how many lines of code 2.9 gigs are. So let me show you one more demo. And what I'm going to show you is an extension. I haven't integrated it back with the other cool GUI tool that I wrote earlier. So I'm hoping to do that when I next have time, but I'll show you anyway. This one I've not done a live demo of before, so this might fail. And it might succeed, we'll see. So build, debug, start without debugging, file. I have the hard code, right now I have a hard-coded path to the test code. So we'll scan, and it comes back and it says things like, hey, you're calling create process insecurely, or the Unicode stack smash pattern. There's a leak in registry handle. This also looks for handle leaks and memory leaks in various shapes and sizes. So the rules for this, this is a raw kind of a test GUI for when I write code, are actually going to be ported back to the other thing, which is, as I mentioned earlier, open sourced and free on GitHub from the current slide. So open source all the things. Caveat, native code rules haven't been integrated. And I should mention that, again, this is open source. This is, me hacking around. This is not check marks. This is not Fortify. I'm not going to stake your organization on this. This is, a tool that I've developed to make my life code reviewing easier and faster and stronger. So the question is, what next after I integrate things? And one of the things I'd like to do is be able to go from static code analysis to working exploit. I don't know how possible that is, how feasible that is. We'll see. Another possibility is, a Visual Studio plugin. Maybe hit tab, build, and it comes up with a security error, and you hit tab and it shows you a possible code fix for this, maybe just an HTML encode or something. And then tab again to complete and actually accept the change into the code. Again, time pending. So that's me. Again, this is on GitHub. In Refactory was an AST generator for the C# aspect of this. I'm John Bull.